Hi everyone, welcome to my channel. In this lesson I would like to introduce an educational package dedicated to the implementation of constant false alarm rate CFAR detector with Vitis high-level synthesis. The package includes design steps, optimization technique, and guidance on integration the IP core into Sync 7000 platform. I would like to start with hardware architecture that I am using in the educational package. So the hardware architecture includes processing system with Cortex-A9 and programmable logic. In programmable logic, there are two high-level synthesis CFAR detectors implemented, namely CFAR, it's a cell averaging CFAR detector, and Ordered-Statistic CFAR detector. So data streaming for both detector by using AXI stream interface and AXI stream switch via AXI DMA. And besides that, both IP cores are fully controllable or runtime configurable by using AXI Lite interface. So therefore, the educational package includes implementation of both fully pipelined runtime configurable CFAR detectors and Vitis high-level synthesis. Integration and runtime configuration of the Xilinx AXI DMA and AXI switch for efficient data transfer. Fixed point input signal simulation and CFAR IP core performance estimation by using Python. And since programmable logic are controllable are running under Linux, so Linux deployment for Sync 7000 with build root also provided. This is the paid content of the educational package. You can contact me in order to get instructions how to obtain all the sources. So the sources includes build root after pre-configuration for Linux deployment with high-level synthesis support, Vitis tickle scripts for automating such projects like Vitis high-level synthesis Vivada and bootloader creation for CD card deployment, Vitis high-level synthesis C++ sources, so for both IP cores, cell averaging, CFAR, and Ordered-Statistic, Python script for fixed point complex input signal simulation and CFAR performance estimation. And besides that, I also offered Linux C API, where I demonstrate how to handle all these IP cores in programmable logic under Linux. In order to leverage the educational package, the following requirements should be met. So as a setup, I'm using RTZ720 board connected via SSH to the host. Host running Ubuntu 20.4 with installed Vitis 2022.2. And besides that, of course, all packages should be installed, all packages required for build root and Vitis 2022.2. So let's turn to architecture for high-level synthesis CFAR IP core implementation. The IP core consists of several sub-modules, sub-blocks. This is a sub-block for reading and writing data to and from AXI stream interface. This is a detector. AVS, square, or log detector can be also implemented. In my implementation, I'm using square detector, shift register, and CFAR processor. The CFAR processor, depending on implementation, can be either cell averaging or Ordered-Statistic. Scale and compare submodel, where the scale factor is provided by using AXI Lite interface. So, as AXI Lite interface is used in order to provide access to IP core registers. So, namely, for example, register with offset 10 is used in order to store and write and read scale factor. AXI stream interface for slave AXI stream interface is a 32 bits, 16 bits for real and 16 bits for imaginary part. And M-axis interface, it's 32 bits with threshold and outcome if a target is detected or not. So let's consider CFAR algorithm scheme in order to get a better understanding which parameters are hard-coded and which parameters are adjustable. So CFAR algorithm scheme assumes a sliding window that comprises several kinds of cells. This is reference cells, guard cells, and cell under test. sliding width slice across the input sample. All samples in reference cells are passed into CFAR processor, where the threshold is calculated, and after scaling, it compares with a cell under test. So here an example how threshold is calculated in a cell averaging CFAR detector. In my implementation, size of GERD cells in the reference cells is a hard-coded parameter, non-adjustable, unlike, for example, scale factor. Scale factor is a fully adjustable runtime configurable parameter. By using the scale factor, probability of false alarm can be adjusted according to noise floor for your system. Let's move to synthesis and implementation report. So synthesis implementation report, first of all, initiation interval. Initiation interval of 1 clock cycle assures fully pipelined implementation of both IP cores. Latency. Latency, basically almost the same. So maybe, Ordered-Statistic CFAR is a little bit delayed data, unlike, for example, cell averaging CFAR. DSP elements. Cell averaging CFAR implementation requires more DSP elements since the threshold calculation that requires a lot of sum, for example, and of course scaling in compare factor. Then the next, it's very interesting. This is flip-flops, LUTs, and shift register LUTs. So these resources are quite different. So especially for example, Ordered-Statistic implementation, this kind of resources required significantly more, unlike, for example, for cell averaging. Why so? Especially, for example, shift register LUTs. So it caused by certain algorithm implemented for Ordered-Statistic CFAR. So the certain algorithm, it's a bitonic sorter. It's a parallel algorithm for sorting data, and this algorithm requires a lot of course, shift resource of flip-flops and LUTs. So it can be it explains why this IP core is significantly heavy compared to cell averaging implementation. Okay, let's consider test procedure of the IP core. So here I have a Vivida block design with two IP cores connected via access stream switch to XCDMA for data transfer. So besides that, both IP cores, as I already mentioned, are fully controllable by using processing system via axial line interface. So in order to work with the IP core, what's needed? So first of all, by using Python, I create binary file. It's input simulated data that should be copied in the target. So besides that, of course, C application also for controlling all this logic should be compiled and also copied on the target. On the target, the C application should be executed, and therefore both outputs of IP cores will be written into output binary files that should be copied back to the host. On the host, by using Python, this binary file will be read and is used in order to estimate performance of the IP core. So, for example, here I have output of the IP cores. So on this plot, I create a simulated signal with uneven noise floor. So noise, approximately minus 33 dB, then noise increase up to 26 dB, and then back to minus 33 dB. Here I set four targets with different position and with different SNR. 10 being with minus 2 dB, then 256 with minus 4, 1018 with minus 8, and 600 with minus 10. This is the outcome of the both IP cores. So first of all targets were detected, but besides that, two false targets were detected. Two false targets by Ordered-Statistic CFAR, and one false target by self-averaging CFAR. So besides that, why basically I set two targets on the edge, because here I would like to demonstrate that the CFAR detector, both CFAR detectors, operates not only on the middle of the input samples, but also including edges of the input sequence. Okay, so let's go through this test procedure. Here I have a target connected to my desktop. Let me check if I can ping one. Okay, yeah, nice. So it means that I can SSH the target. Here I have three folders. I'm interested in this folder since okay, I will remove all files here. So I don't need this one, and what I have here, and I don't need application CFAR test. Okay, so first of all, what I need is I need to reconfigure my programmable logic part from Linux. For doing this, I have CFAR init shell script. Okay, and let's go to create first input data. So Python CFAR. Okay. Yeah. So here are my input samples with 4 targets, and so every target has certain position and certain SNR. Okay, let's close this. The binary file is created in sim file input. Let's copy this to the target. Sim and the in copy to CFAR folder. Okay, and let's compile the application. So the application is placed in the CFAR folder. Okay, here we are, just run a make. Okay, it's ready. Let's copy this CFAR test to the target. CFAR. Okay, and let's go to the target. So here I have input file, and here I have an application. So therefore, application can be executed here. CFAR test. Let's run. Okay, finish. Here, yeah, we can estimate performance. So basically, we can run one more time because it's a Linux and time can be different, but nevertheless, transfer time is yeah, almost the same, maybe Ordered-Statistic a little bit longer, since it has greater latency as self-averaging CFAR implementation, but yeah, nevertheless. Okay, several times, and so here I have two binary files, the output from both IP cores. Let's copy it back to the host. SCP root. Okay, so and here I have the CFAR, the out files in the sim folder. Okay, both files are here, and let's call again Python script. But the Python script should consist a little bit different flag. It's a 1 because I would like to read output. Okay, so yeah, here's my output. Yeah, in this case, all 4 targets were detected correctly. Unlike, for example, from the PPTX slide, so all 4 targets. Basically, how I set an output. Output, it's a threshold itself, and in case if I have if threshold is exceeded by the target, so I will provide a high value here. So this is how it works. Of course, it can be modified just to supply decision, for example, whether the target is detected or not, for example. But here, for demonstration purpose, it's again threshold plus plus decision, so whether the target is detected or not. So in blue color, this is the input signal, and yeah, red color, Ordered-Statistic CFAR, and in green color, this is a cell aberration CFAR. Okay, I hope the lesson was quite interesting. I wish you good luck with your embedded design. And if you would like to boost, your experience, your expertise, please feel free to contact me in order to obtain sources for this educational package. Ciao.